In statistics and econometrics, particularly in regression analysis, a dummy variable is one that takes the value 0 or 1 to indicate the absence or presence of some categorical effect that may be expected to shift the outcome. Dummy variables are used as devices to sort data into mutually exclusive categories. For example, in econometric time series analysis, dummy variables may be used to indicate the occurrence of wars or major strikes. A dummy variable can thus be thought of as a truth value represented as a numerical value 0 or 1. Dummy variables are proxy variables or numeric stand-ins for qualitative facts in a regression model. In regression analysis, the dependent variables may be influenced not only by quantitative variables, but also by qualitative variables. A dummy independent variable which for some observation has a value of 0 will cause that variable's coefficient to have no role in influencing the dependent variable, while when the dummy takes on a value 1 its coefficient acts to alter the intercept. For example, suppose gender is one of the qualitative variables relevant to a regression. Then, female and male would be the categories included under the gender variable. If female is arbitrarily assigned the value of 1, then male would get the value 0. Then the intercept would be the constant term for males but would be the constant term plus the coefficient of the gender dummy in the case of females. Dummy variables are used frequently in time series analysis with regime switching, seasonal analysis and qualitative data applications. Dummy variables are involved in studies for economic forecasting, biomedical studies, credit scoring, response modeling, etc. Dummy variables may be incorporated in traditional regression methods or newly developed modeling paradigms. Incorporating a dummy independent variable. Dummy variables are incorporated in the same way as quantitative variables are included in regression models. For example, if we consider a regression model of wage determination, wherein wages are dependent on gender and years of education, wage equals I plus or minus 0 plus I0 female plus I plus or minus 1 education plus U. In the model, female equals 1 when the person is a female and female equals 0 when the person is male. I0 can be interpreted as the difference in wages between females and males, keeping education and the error term U constant. Thus, I0 helps to determine whether there is a discrimination in wages between men and women. If I0 less than 0, then for the same level of education, women earn a lower wage than men. On the other hand, if I0 greater than 0, then women earn a higher wage than men. Note that the coefficients attached to the dummy variables are called differential intercept coefficients. The model can be depicted graphically as an intercept shift between females and males. In the figure, the case I0 less than 0 is shown. Dummy variables may be extended to more complex cases. For example, seasonal effects may be captured by creating dummy variables for each of the seasons, D1 equals 1 if the observation is for summer, and equals 0 otherwise. D2 equals 1 if and only if autumn, otherwise equals 0. D3 equals 1 if and only if winter, otherwise equals 0. And D4 equals 1 if and only if spring, otherwise equals 0. In the panel data fixed effects estimator dummies are created for each of the units in cross-sectional data or periods in a pooled time series. However, in such regressions either the constant term has to be removed, or one of the dummies removed, making this the base category against which the others are assessed. For the following reason, a precaution needs to be taken while using dummy variables for calculating the regression coefficients. The constant terms in all the regression equations will obviously have a coefficient of 1. When the regression is expressed as a matrix equation, the columns of the coefficient matrix will be linearly dependent. In fact, the column rank of the matrix is reduced by 1 for every categorical variable. As a result, the regression equation will be unsolvable even by the typical pseudo-inverse method. In other words, if the vector of one's variable were also present, this would result in perfect multicollinearity, so that the matrix inversion in the estimation algorithm would be impossible. This is referred to as the dummy variable trap. The solution is to drop one term from the equation for each set of dummy variables representing a categorical variable. ANOVA models. A regression model in which the dependent variable is quantitative in nature but all the explanatory variables are dummies is called an analysis of variance model. ANOVA model with one qualitative variable. Suppose we want to run a regression to find out if the average annual salary of public school teachers differs among 3 geographical regions in country A with 51 states, north, south, west. Say that the simple arithmetic average salaries are as follows: $24,424.14, $22,894, $26,158.62. The arithmetic averages are different, but are they statistically different from each other? To compare the mean values, analysis of variance techniques can be used. The regression model can be defined as y equals I plus or minus 1 plus I plus or minus 2d 2i plus I plus or minus 3d 3i plus e, where y equals average annual salary of public school teachers in state I, d2i equals 1 if the state I is in the north region, d2i equals 0 otherwise. d3i equals 1 if the state I is in the south region, d3i equals 0 otherwise. In this model, we have only qualitative regressus, taking the value of 1 if the observation belongs to a specific category and 0 if it belongs to any other category. This makes it an ANOVA model. Now, taking the expectation of both sides, we obtain the following: mean salary of public school teachers in the north region, E, d2i equals 1, d3i equals 0, equals I plus or minus 1 plus I plus or minus 2, mean salary of public school teachers in the south region, E, d2i equals 0, d3i equals 1, equals I plus or minus 1 plus I plus or minus 3, mean salary of public school teachers in the west region, E, d2i equals 0, d3i equals 0, equals I plus or minus 1. The error term does not get included in the expectation values as it is assumed that it satisfies the usual OLS conditions, that is, E equals 0. The expected values can be interpreted as follows: the mean salary of public school teachers in the west is equal to the intercept term I plus or minus 1 in the multiple regression equation and the differential intercept coefficients, I plus or minus 2 and I plus or minus 3. Explained by how much the mean salaries of teachers in the north and south regions vary from that of the teachers in the west. Thus, the mean salaries of teachers in the north and south is compared against the mean salary of the teachers in the west. Hence, the west region becomes the base group or the benchmark group, that is, the group against which the comparisons are made. The omitted category, that is, the category to which no dummy is assigned, is taken as the base group category. Using the given data, the result of the regression would be, angstrom paragraph I equals 26,158.62 or 1,734.473 d2ia 3,264.615 d3i, say equals, t equals, p equals, r2 equals 0.0901, where, say equals standard error, t equals t statistics, p equals p-value. The regression result can be interpreted as, the mean salary of the teachers in the west is about $26,158, the salary of the teachers in the north is lower by about $1,734 and that of the teachers in the south is lower by about $3,265. To find out if the mean salaries of the teachers in the north and south are statistically different from that of the teachers in the west, we have to find out if the slope coefficients of the regression result are statistically significant. For this, we need to consider the p-values. The estimated slope coefficient for the north is not statistically significant as its p-value is 23%. However, that of the south is statistically significant at the 5% level as its p-value is only around 3.5%. Thus the overall result is that the mean salaries of the teachers in the west and north are not statistically different from each other, but the mean salary of the teachers in the south is statistically lower than that in the west by around $3,265. The model is diagrammatically shown in Figure 2. This model is an ANOVA model with one qualitative variable having three categories. ANOVA model with two qualitative variables, Suppose we consider an ANOVA model having two qualitative variables, each with two categories. Hourly wages are to be explained in terms of the qualitative variables marital status and geographical region. Here, marital status and geographical region are the two explanatory dummy variables. Say the regression output on the basis of some given data appears as follows. Angstrom paragraph I equals 8.8148 plus 1.0997 D2 or 1.6729 D3, where Y equals hourly wages, D2 equals marital status, 1 equals married, 0 equals otherwise, D3 equals geographical region, 1 equals north, 0 equals otherwise. In this model, a single dummy is assigned to each qualitative variable, one less than the number of categories included in each. Here, the base group is the omitted category, unmarried, non-north region. All comparisons would be made in relation to this base group or omitted category. The mean hourly wage in the base category is about $8.81. In comparison, the mean hourly wage of those who are married is higher by about $1.10 and is equal to about $9.91. In contrast, the mean hourly wage of those who live in the North is lower by about $1.67 and is about $7.14. Thus, if more than one qualitative variable is included in the regression, it is important to note that the omitted category should be chosen as the benchmark category and all comparisons will be made in relation to that category. The intercept term will show the expectation of the benchmark category and the slope coefficients will show by how much the other categories differ from the benchmark category. ANCOVA models. A regression model that contains a mixture of both quantitative and qualitative variables is called an analysis of covariance model. ANCOVA models are extensions of ANOVA models. They are statistically controlled for the effects of quantitative explanatory variables. To illustrate how qualitative and quantitative regresses are included to form ANCOVA models, suppose we consider the same example used in the ANOVA model with one qualitative variable, average annual salary of public school teachers in 3 geographical regions of country A. If we include a quantitative variable, state government expenditure on public schools per pupil, in this regression, we get the following model. Y equals I plus or minus 1 plus I plus or minus 2 D2 I plus I plus or minus 3 D3 I plus I plus or minus 4 I plus E, where Y equals average annual salary of public school teachers in state I, Xi equals state expenditure on public schools per pupil, D2I equals 1, if the state I is in the North region. D2I equals 0, otherwise. D3I equals 1, if the state I is in the South region. D3I equals 0, otherwise. Say the regression output for this model is, Angstrom paragraph I equals 13,269.11 or 1,673.514 D2IA 1,144.157 D3I plus 3.2889 Xi. The result suggests that, for every $1 increase in state expenditure per pupil on public schools, a public school teacher's average salary goes up by about $3.29. Further, for a state in the North region, the mean salary of the teachers is lower than that of West region by about $1,673 and for a state in the South region, the mean salary of teachers is lower than that of the West region by about $1,144. Figure 3 depicts this model diagrammatically. The average salary lines are parallel to each other by the assumption of the model that the coefficient of expenditure does not vary by state. The trade-off shown separately in the graph for each category is between the two quantitative variables, public school teachers' salaries in relation to state expenditure per pupil on public schools. Interactions among dummy variables. Quantitative regresses in regression models often have an interaction among each other. In the same way, qualitative regresses, or dummies, can also have interaction effects between each other, and these interactions can be depicted in the regression model. For example, in a regression involving determination of wages, if two qualitative variables are considered, namely, gender and marital status, there could be an interaction between marital status and gender. These interactions can be shown in the regression equation as illustrated by the example below. with the two qualitative variables being gender and marital status and with the quantitative explanator being years of education. A regression that is purely linear in the explanators would be y equals I squared 1 plus I squared 2d2, I plus I squared 3d3, I plus or minus psi plus e, where I denotes the particular individual, y equals hourly wages, x equals years of education, d2 equals 1 if female, 0 otherwise, d3 equals 1 if married, 0 otherwise. This specification does not allow for the possibility that there may be an interaction that occurs between the two qualitative variables, d2 and d3. For example, a female who is married may earn wages that differ from those of an unmarried male by an amount that is not the same as the sum of the differentials for solely being female and solely being married. Then the effect of the interacting dummies on the mean of y is not simply additive as in the case of the above specification, but multiplicative also, and the determination of wages can be specified as y equals I squared 1 plus I squared 2d2, I plus I squared 3d3, I plus I squared 4d2, it 3, I plus or minus psi plus e. Here, I squared 2 equals differential effect of being a female, I squared 3 equals differential effect of being married, I squared 4 equals further differential effect of being both female and married. By this equation, in the absence of a non-zero error, the wage of an unmarried male is I squared 1 plus I plus or minus psi, that of an unmarried female is I squared 1 plus I squared 2 plus I plus or minus psi, that of being a married male is I squared 1 plus I squared 3 plus I plus or minus psi, and that of being a married female is I squared 1 plus I squared 2 plus I squared 3 plus I squared 4 plus I plus or minus I. Thus, an interaction dummy can alter the dependent variable from the value that it gets when the two dummies are considered individually. However, the use of products of dummy variables to capture interactions can be avoided by using a different scheme for categorizing the data, one that specifies categories in terms of combinations of characteristics. If we let d4 equals 1 if unmarried female, 0 otherwise, d5 equals 1 if married male, 0 otherwise, d6 equals 1 if married female, 0 otherwise, then it suffices to specify the regression, y equals I1 plus I4 d4, I plus I5 d5, I plus I6 d6, I plus or minus psi plus e. Then with zero shock term the value of the dependent variable is I1 plus I plus or minus psi for the base category unmarried males, I1 plus I4 plus I plus or minus psi for unmarried females, I1 plus I5 plus I plus or minus psi for married males, and I1 plus I6 plus I plus or minus psi for married females. This specification involves the same number of right-side variables as does the previous specification with an interaction term, and the regression results for the predicted value of the dependent variable contingent on xi, for any combination of qualitative traits, are identical between this specification and the interaction specification. Dummy dependent variables. What happens if the dependent variable is a dummy? A model with a dummy dependent variable is one in which the dependent variable, as influenced by the explanatory variables, is qualitative in nature. Some decisions regarding how much of an act must be performed involve a prior decision-making on whether to perform the act or not. For example, the amount of output to produce, the cost to be incurred, etc. involve prior decisions on whether to produce or not, whether to spend or not, etc. Such prior decisions become dependent dummies in the regression model. For example, the decision of a worker to be a part of the labor force becomes a dummy dependent variable. The decision is dichotomous, that is, the decision has two possible outcomes, yes and no. So the dependent dummy variable participation would take on the value 1 if participating, 0 if not participating. Some other examples of dichotomous dependent dummies are cited below. Decision choice of occupation. Dependent dummy, supervisory equals 1 if supervisor, 0 if not supervisor. Decision, affiliation to a political party. Dependent dummy, affiliation equals 1 if affiliated to the party, 0 if not affiliated. Decision, retirement. Dependent dummy, retired equals 1 if retired, 0 if not retired. When the qualitative dependent dummy variable has more than two values, it becomes a multi-response or a multinomial or polycotomous model. Dependent dummy variable models. Analysis of dependent dummy variable models can be done through different methods. One such method is the usual OLS method, which in this context is called the linear probability model. An alternative method is to assume that there is an unobservable continuous latent variable y and that the observed dichotomous variable y equals 1 if y 0, 0 otherwise. This is the underlying concept of the Logit and Probit models. These models are discussed in brief below. Linear probability model. An ordinary least squares model in which the dependent variable y is a dichotomous dummy, taking the values of 0 and 1, is the linear probability model. Suppose we consider the following regression, y equals I plus or minus 1 plus I plus or minus 2 xi plus e, where x equals family income, y equals 1 if a house is owned by the family, 0 if a house is not owned by the family. The model is called the linear probability model because the regression is linear. The conditional mean of y given xi, written as y xi, is interpreted as the conditional probability that the event will occur for that value of xi that is, pr, y equals 1 xi. In this example, xi gives the probability of a house being owned by a family whose income is given by xi. Now, using the OLS assumption e equals 0, we get xi equals I plus or minus 1 plus I plus or minus 2 xi. Some problems are inherent in the LPM model. 1. The regression line will not be a well-fitted one and hence measures of significance, such as a 2, will not be reliable. 2. Models that are analyzed using the LPM approach will have heteroscedastic disturbances. 3. The error term will have a non-normal distribution. 4. The LPM may give predicted values of the dependent variable that are greater than 1 or less than 0. This will be difficult to interpret as the predicted values are intended to be probabilities, which must lie between 0 and 1. 5. There might exist a nonlinear relationship between the variables of the LPM model, in which case, the linear regression will not fit the data accurately. Alternatives to LPM. To avoid the limitations of the LPM, what is needed is a model that has the feature that as the explanatory variable, xi, increases, pi equals e should remain within the range between 0 and 1. Thus the relationship between the independent and dependent variables is necessarily nonlinear. For this purpose, a cumulative distribution function can be used to estimate the dependent dummy variable regression. Figure 4 shows an S-shaped curve, which resembles the CDF of a random variable. In this model, the probability is between 0 and 1 and the non-linearity has been captured. The choice of the CDF to be used is now the question. Two alternative CDFs can be used, the logistic and normal CDFs. The logistic CDF gives rise to the Logit model and the normal CDF give rises to the Probit model. Logit model. The shortcomings of the LPM led to the development of a more refined and improved model called the Logit model. In the Logit model, the cumulative distribution of the error term in the regression equation is logistic. The regression is more realistic in that it is nonlinear. The Logit model is estimated using the maximum likelihood approach. In this model, p, y equals 1x, which is the probability of the dependent variable taking the value of 1 given the independent variable is, where xi equals I plus or minus 1 plus I plus or minus 2 xi. The model is then expressed in the form of the odds ratio. What is modeled in the logistic regression is the natural logarithm of the odds being defined as p/1p. Taking the natural log of the odds, the logit is expressed as. This relationship shows that Li is linear in relation to xi, but the probabilities are not linear in terms of xi. Probit model. Another model that was developed to offset the disadvantages of the LPM is the Probit model. The Probit model uses the same approach to nonlinearity as does the Logit model. However, it uses the normal CDF instead of the logistic CDF. See also, Chow test, hypothesis testing, indicator function, linear discriminant function, multicollinearity, Probit model, references. External links, http www.statYaleEdu 1997-98 ANOVA Reg HTM, http Udley-Dustate ANCOVA HTML, http StatETH Sedge Teaching Handouts Chapter 7 PDF, http Socks of McMaster Kakus's Dummy Regression Notes PDF, http HSP-MSP-HSC EduJ 716716 to 6% 20 dummy %20 variables %20 and %20 time %20 series PDF.